what? Zeros of polynomial functions. You already know about zeros. What's a zero of a function? The x-intercept. So graphically, a zero is an x-intercept. What does it mean for the function if you have a zero? I say, hey, 2 is a zero of that function. What's it mean? If x equals 2, y equals 0, that's exactly what it means. That's what a zero is. Now, there are other names for zeros. Roots, x-intercepts, solutions, answers. All those things mean the same thing. Why do you have so many? I don't know. Somebody decided. I don't know. I didn't make those decisions. For each of the graphs below, state the end behavior and the zeros. All right, end behavior. You know what that means? Where it's going, where the great. Okay, that was hilarious. It means what's happening as x approaches infinity and as x approaches negative infinity. What are the y values doing? We are not super formal in this class, in your writing. Let's just go through this. F of x is a cubic function. Now I'm right here. Left end behavior. Left end, does that mean as x approaches infinity or negative infinity? Negative infinity. So left end behavior, you're going to say as x approaches negative infinity, what does f of x approach? Negative infinity. Right end behavior. As x approaches infinity, what does this function do? Approaches infinity, right. Does it? Yeah. What are the zeros? -2, -1, and 1. And I can put plus or minus 1 there if I wanted to. Please put x equals, because zeros are always x values. Let's look at g of x. Let's talk about end behavior. Do you know the term quartic? That means degree 4, right. Left end behavior. As x approaches negative infinity, oops, this is g of x. G of x approaches what? Infinity. Now I'm going to tell you what we say in calculus. We would say as x approaches negative infinity, this function increases without bound. Increases without bound, meaning it just keeps increasing. You finished with that, Sam? I'll take it out anyway. The function increases without bound. We good? Okay. What's the right end behavior on this function? As x approaches infinity, g of x also approaches infinity, or g of x also increases without bound. Go ahead. Has everybody had the hole punch? Okay. What are the zeros of g of x? Roughly -2.5 and 2. Now wait a minute. How many answers should that have? It better have 4 because that's a quartic. That's a degree 4. Wait a minute. It looks like it's at 2 for a while. What we're going to talk about is how you can look at that graph and say, oh, I can tell how many times 2 is a root, is a 0. I'm pretty sure you've never done that before. Say that again?
Is that where it's like x minus 1 squared?
You'll have to show me. When we get there, I think maybe you can answer your question because I'm not quite sure. Quintic, degree, right. Left end behavior. As x approaches negative infinity, h of x approaches what? Negative infinity. Or we say in calculus, decreases without bound. Right end behavior. As x approaches positive infinity, h of x approaches infinity. What are the zeros? -4, -2, 2, and 5. Right. How many zeros did we find? 4. How many ought there be? 5. Where's the other one?
We'll figure it out.
Okay. First of all, let's go ahead, Malin.
Okay, isn't it when you keep throwing the zeros, isn't it because like you have to zoom in a lot? Like on the graphic up here, I think.
Sometimes. The answer to that is sometimes, yes. Okay, let's talk about end behavior here for just a minute. What did you notice on f of x? On the end behavior, the ends went different ways, right? And that happened on your cubic, and it also happened on your quintic, correct? But on the quartic, the ends went the same way, didn't they? Wonder why that is. Okay. Here's the issue. If I have a quartic, if I have a degree 4, I put in a big positive number. And I put in the same big number, but it's negative. And I have a degree 4. Am I going to get the same answer, or am I going to get opposite answers? Same, because if I raise a negative number to an even power, I get a positive answer. If I take a negative number and raise it to an odd power, I get a negative. So when that exponent, when it's I can't even talk, when it's quintic, degree 5, my ends are going to go different ways, because a negative number raised to a big power is negative, but the positive number raised to a big power is positive. Now, I heard somebody say the word multiplicity a minute ago. Am I assuming you know what that means?
Like how many times a zero? Yeah, x equals a comma.
It's how many times, I don't know what's on the notes, but it's essentially how many times a 0 is actually a 0. What does it say on the notes?
The number of times is a root
How many times x minus a is a root?
of x minus 2 here.
Does it say x minus 2 in your notes?
I just figured out 0.
Oh, okay. So it's how many times a 0 is actually a 0. Now, you're given some information right here. So I'm going to have to go back and forth. Look at the graph of f. All the zeros have multiplicity 1. All of these zeros right here have multiplicity 1. Look at G. The 0 of negative 2.5 has a multiplicity 1, and x equal 2 has a multiplicity 3. 1, and here 3 times. In this one, you can check me because you can read what's on the bottom of your page. Negative 4 has a multiplicity of 1. Negative 2 has a multiplicity of 1. 2 has a multiplicity of 2, and 5 has a multiplicity of 1. Now, I want you to look at this. What's the sum of those numbers? 3. Oh my gosh. What's the sum of those numbers? Oh my gosh. What's the sum of those numbers? Oh my gosh. Now, I don't know what the questions are on the next page. We'll get there in a minute. But we're just going to talk a little bit. Look at how a multiplicity 1 root crosses the x-axis versus how a multiplicity 3 root does, or how a multiplicity 2 root does. Do you see how they're different in how they cross or touch the x-axis? Do you see anything different?
Yes.
Tell me something you see. Wayne? You started talking as soon as I said Wayne, you quit talking. Tell me something you see.
Like it has a multiplicity of 1. It's like,
It just crosses,
yeah, it
right?
just crosses.
Yeah, just crosses. Oh, that's well said. That's well said. Doesn't linger there, huh? It just goes on, goes about its business, right? That's a good one. What else? Ah, a multiplicity of 2 didn't cross the x-axis, did it? It kissed the x-axis and went back where it came from. Huh? Huh? Any of you guys, when you were little kids on the playground, you run over, kiss a girl, and run off? Okay. Sam did. I bet Sam did. So look, a multiplicity of 2, the function's just going to kiss that x-axis and then go back where it came from. What about a 3? That's kind of funky, isn't it? Now, there are some terms that you need to know, and this is, I don't know of a better way to teach this than just to tell you some new terms. Notice that the graph went from looking like that to looking like that. Let's talk about this piece right here. When you have a curve that would shed water if it got rained on, that graph is called concave down. Concave down. When you have a graph that would catch water, that's called concave up. Do you see that right at that 0, right there, that's where the function changes from shedding water to catching water? Does that make sense at all? That, ladies and gentlemen, is called a point of inflection. You don't need to write that down yet. It'll come later. But that's what it's called. So when you have a multiplicity of 3, your graph will cross the x-axis, but your concavity will change. Concavity? What the heck is concavity? Concavity, you have concave up, catches water, concave down, sheds water. That's concavity. And when you have multiplicity of 3, that point is where the graph changes from catching water to shedding water. Next page. We may have answered a bunch of these questions. We've already answered those questions. Okay, so listen. So you can fill this in later. What do you notice about the sum of the multiplicities of the zeros and the degree of the function? They are the same. Describe the behavior of a graph as it approaches a 0 whose multiplicity is 1. Just say, yeah, the graph just crosses the x-axis smoothly. I don't know what the notes say, but something like that. Number 3, describe the behavior of a graph as it approaches a 0 whose multiplicity is 2. The function kisses the x-axis, but does not cross. Multiplicity 3, the concavity changes at that 0. You might think it lingers, the graph lingers there a little bit. All right. For each of the following functions, you are given a factor of the function. Identify the 0 associated with that factor. What's the 0 associated with this factor? Then use synthetic division to determine how many times the given factor is a factor of the function. Question, is that necessary when we're looking at that graph?
No.
When x is -1, what does the graph look like at x equal -1? Just crosses. What's this multiplicity? 1. Describe the behavior. The graph just crosses the x-axis. That's all it does. Nothing interesting. But let's talk about something else here. Yeah, you've got the filled in notes, but you know what? Sometimes I just got other stuff to say because I just want to say it. How many zeros is this going to have? 3. How many zeros do you have? You can see 3. There is no way that -1 is a root more than once. No way. Next one. What 0 is associated with the factor of x minus 1? Look at the graph. What's the multiplicity of the 0 of 1? 2. Why? The function kisses the x-axis but does not cross. Could you defend that answer just by looking at the graph? This one has to have a multiplicity of 2 because the graph kisses the x-axis, but what's the multiplicity of that 0? 1, and 1 plus 2 is 3, and that's all the roots we've got. Is that all that's on that page? Well, heck. Oh, okay, good. How many roots is p of x going to have? 4. 4. This is getting old. What root is associated with the factor of x minus 1? How many times is x equal 1 a factor? 3 times. Why?
Because the point of inflection changes.
Because the concavity changes. The concavity yes, at the point of inflection. Right. So the concavity changes. Now you tell me. This part. Is that part concave up or concave down? Up catches water. So this part is concave down. There you go. Well done. Now let's consider how we might be able to locate the zeros of a polynomial function numerically. What you are getting ready to learn is essentially something that in calculus we call the intermediate value theorem. Now I'm going to give you an example of the intermediate value theorem. Corey, how tall are you?
6 foot.
6 foot. Do you remember how tall maybe you were in like the 9th grade? You got any idea?
4 or 5.
Okay. So, let me, I'll do this so in case anybody's watching. So, I don't want you to draw this. I just want to show you what I'm talking about. If I put on the x-axis Coy's year in school, and I put on the y-axis Coy's height. You're a senior, right? Senior. As a senior, Coy is 6 feet tall. let's say that in the ninth grade, I'm gonna put ninth grade way over here, okay? Let's say in the ninth grade, Coy was 5'7". Now I'm gonna ask you what seems like a dumb question. Was Coy ever 5'10"?
Yes.
When? What? How do I connect the dots? In a straight line? In a curve? Straight line. Are you sure his growth was linear, where he gained exactly the same amount of height every day over those years? I'm pretty sure I was like, 5 feet tall for about 30 seconds, and then I kept growing, right? No, it will not go back down. We hope. We hope it will not go back down. Now, this is going to sound funny to you. The intermediate value theorem. Do you need to know that in pre-cal? No. It's what you're going to learn. You're just not going to learn the name. All right? The intermediate value theorem says, I know that if Coy was 5'7" when he was in the 9th grade and he's 6 feet tall in the 12th grade, there was some time between 9th grade and 12th grade where he was 5'10". You buy it?
Yes.
Huh?
Let's say he grew like 4 inches over time.
Okay, so during that night, he would have still been 5'10" and for some matter of seconds. Could he have skipped 5'10"? No. Impossible. Now, why is that impossible? Because age is what we call a continuous function. You never have to lift your pencil. The intermediate value theorem says, I know that at some point he was 5'10", but I don't know when it was. The intermediate value theorem is what we call an existence theorem. I know it happened, I just don't know when. Okay? Oh, just wait till you take calculus and you'll see. You can take it in college. Because you're just, what's going to stay with you is I've got to find out the answer to that question. So you're going to go to calculus in college and you're going to take it. Okay.
I don't think it goes.
Depends on your major.
That's enough.
Consider this function. Now, we talked about this function earlier. Graph is here. Find each pair of function values in the table below and answer the following questions. Here's what I want you to do. I want U3 and U4 to find h of -2 and h of -1. I want the rest of you guys to find h of 0 and h of 2. Now, you guys are thinking, you got the easy part because you got h of 0. Well, go. I don't know what to say. Go. Here's what I want you to do. Make sure you write down the answers from the other group. So you guys, make sure you write down in this box h of 0 equals 3 and h of 2 equals 7. You over here, make sure you write down h of -2 equals -9 and h of -1 equals 7. And I'm assuming I'm right because nobody's told me different. That's because nobody wants to hurt my feelings. Hurt them. I got to know if I'm right or not. Oh, that's because I... Thank you. All right, let's go down to this question. From the graph, did I screw something up now? I forgot to do some recording, but I'm not sure how much I forgot. For those of you who are gone today, I will post this, but I'll record when I teach this on Monday, and I'll post the better one. Hopefully I won't forget any then. Dang it. You guys have to help me. Help me on that. For some reason, I don't know why, today, my this thing right here disappears. I don't know what. I don't know. Okay, the table of values represents values of a quartic function. How many zeros should you have on a quartic function? 4. Now let's look at this. The function has a negative root and 3 positive roots. So look at what you're told. We got a negative root and we got 3 positive roots. So we're going to go answer some questions. Are any of the roots of f of x specifically identified in the table? Can I look at the table and say, I know I've got a root at x equals y1? Because y equals 0. Good. At x equal 1 because y equals 0. What is the multiplicity of this root? Now remember, when you look at Sparks, that's the guy who wrote the curriculum, when you look at his tables, you have to assume that the pattern doesn't change, meaning something funky doesn't happen in between 2 values you've got. Why do you think the multiplicity would be 2? Because what's negative on both sides of it? The y values. You see that the y values are the same sign on both sides of x equal 1? So to us it looks like that function's going to come up, kiss the x-axis, and come back. So we think the multiplicity is 2 because the sign of the y values is negative on both sides of x equal 1. Tell me if you don't understand, okay? Anybody need more time there? Question?
So like, it's quartic. Where's the other 2?
That's what we're going to talk about on these next questions. That's a good question, though. Let's look at number 2. Between which 2 x values in the table is the negative root located? Why is the negative root between -4 and -1? In the, well, that's beautifully said. There's a sign change in the y values, or the y values change sign. Good. So we know we have a root between x equals -4, was it -1? Because the y values change sign. How many roots have we accounted for so far? We've accounted for 2 here and 1 here. So we've accounted for 3 of them. Look at number 3. Between which 2 x values in the table is the second distinct, please look at that word, distinct. Distinct means different. Positive root located. Why between x equal 3 and x equal 5? Beautiful. Between x equal 3 and x equal 5? Because the y values change sign. Sarah, does this answer your question? You learned the intermediate value theorem. You learned about multiplicity. You firmed up your understanding of end behavior, I think. Let's take a short break. Let me tell you how much of this next section I'd like to do. I would like for us to do today a first page, the back of the first page, and the very, very top of the next page. That's what I'd like to get through. Question? These are also posted because there's a lot of writing here. If you have looked at the second lesson, now it's posted in a different, you'll have to get out of it. It's not posted as one post, but there's a lot of writing. Now, I think the author gets wordy here, but that's just an opinion. So again, please pay attention to the filled-in notes and go back later and fill them in if you feel like you need to. You will not be quizzed on this material on Tuesday. You will not. Determine what type of polynomial functions are graphed. Are they quadratic? Are they cubic? Are they quartic? Are they quintic? We're not going above that. Defend your answer. Question? Yes. Was that your question? No, I'm kidding. Go ahead. Go ahead, Lily. Tuesday. Your quiz is Tuesday. Did I say Monday? Next time we meet, whenever that is. It's absolutely doable. Terminology associated with graphs of polynomial functions. I've already taught you concavity, concave up, concave down. We summed up the term point of inflection a little bit. Determine what type of polynomial function we have and give a reason for your conclusion based on the zeros of the function. Look at F. Please do not write all this down. Please wait till later. What kind of function do you think F is? Cubic. Why? Because, tell me where the zeros are. What is the multiplicity of the root 0? Because the curve crosses, just smoothly crosses. What is the multiplicity at 3? Because what does the graph do? Good. So we know we have a cubic function because we have a 0 of multiplicity 1 and a 0 of multiplicity 2. Right? Now, Braden said something. He said the end behaviors are different. So that does tell us that that degree is going to be odd, right? But I think the instructions said based on zeros. Look at G. What kind of graph do you think G is? If it's quartic, how many zeros do you have? 4. So let's go left to right. I think I see a 0 at -3. What's its multiplicity? Because the curve crosses the x-axis. I see a 0 at x equals 0. Multiplicity? Because kisses. I see a 0 at 3. Multiplicity? 1. So the sum of those multiplicities, 1 plus 2 plus 1, is 4. The thing is quartic.
You just guess by counting how many times the squiggles change.
That is how we did it before. Now we're going to do it.
But you still get the right answer.
You will. You will get the right answer. He's just going to keep counting squiggles, and I'm going to keep counting that wrong. So, all right. No, I'm not meaning to be mean, Braden. I'm not meaning to be mean, I promise. H of x. Come on. You're just going to walk out. H of x. Quintic. You have, let's go left to right. You have a 0 of multiplicity. I don't know what happened there. You have a 0 of multiplicity 2, multiplicity 1, multiplicity 2, and the sum of 2 and 1 and 2 is 5. All right. I know you are. I know you are. It's why I wanted you in this class. You got to do this before you take calculus. You have already been exposed to identifying certain graphical properties of a function. This better be all review. What's the domain of that function? All real numbers. Good. What's the range of this function? X is y. Range is y.
I wrote it down correctly.
-4 to infinity. Let's just talk it. Let's not write it. Let's talk it. As x approaches negative infinity, the function approaches infinity. As x approaches positive infinity, the function approaches infinity. Good. And the end behavior is the same because the degree of this function is even because it's a quartic. 1, 2, 3, 4. Yeah. 1, 2, 3, 4. Right? Changing the squiggles.
1, 2, 3 plus 1.
There you go. There you go. There you go. Oh, you'll learn all kinds of cool stuff about that next year in calculus. Okay. Identify. Just saying. Identify the intervals where p of x is negative. Graphically, what does it mean for p of x to be negative? Below the x-axis, because that's where the y values are negative. Well done. Where does that happen?
Oh, no, I have to figure it out. 3 to 0.
Why did we not include 0?
Never crosses.
Because the y value is equal to 0 there. The y value is equal to 0 there. You should be able to do that part. Look at the last question here. On what intervals along the x-axis is p of x increasing? This function is increasing where? Now, do you remember I've told you only use parentheses when you do increasing and decreasing. You want to know why? Take calculus. Because calculus explains why. Okay. Calculus does explain why. I promise it does. Decreasing. Where's that function decreasing? From infinity to negative 2? Negative infinity to negative 2, right? And because, never mind, I don't want a because there. Never mind. I'm so used to in calculus, we defend everything. All right. You've heard the terms maximum and minimum. Have you heard the terms relative maximum and minimum? Because if I had read, okay. Has anybody else ever mentioned that as in terms of in a class? Have you ever heard relative max or min ever before? Where did you? You've had college algebra? Oh, well, snap. All right. Good. Okay. So, yeah, no wonder. A relative maximum, the easiest way to understand a relative maximum or a relative minimum. A relative maximum is a hill. A relative minimum is a valley. A relative maximum is any place that your graph changes from increasing to decreasing. A relative minimum is any place that your graph changes from decreasing to increasing. That's it. Huh? Yes. Will be a point. So, define relative maximum. Don't write all this down, we don't have time. A relative maximum is where your graph changes from increasing to decreasing. It's a hill. Look at these two graphs. Where are your hills? At x equals where? First one. You only have one relative maximum. Look at the second. Where are your hills? X equal negative 2 and x equal 2. Good. You'd have two hills. You have two places where the graph changes from increasing to decreasing. The relative minimum is a valley. It's where your graph changes from decreasing to increasing. Look at the first one. Do you see any relative minimums?
Yes, 3.
X equals 3. Do you see any relative minimums in this quartic? X equals positive and negative 2. Good, because you have decreasing to increasing, decreasing to increasing. Questions? All right. Look at this one on your filled in notes. An absolute minimum is absolutely the lowest point on that graph. You hear me? I want you to look at this first one. What is the absolute minimum? Negative infinity is not a number.
Okay.
What's the lowest y value on that graph? There isn't one.
Oh, okay. Oh, yeah, because
Don't-
the arrow.
Doesn't that function continue to decrease without bound?
Yeah.
There is no absolute minimum here because there is not a lowest point on that curve. Look at the second one. Oh, that's a relative minimum, but it's not the lowest point on that curve. Not on this first graph, no. Let's go to the second graph. Does this graph have an absolute minimum? At x equals? At x equal 2. Now, does this graph have a relative minimum? At?
0.5.
Now, here's minimum. Minimum. Now, here's what I want you to understand. That's a relative minimum, and that's a relative minimum. Why is this both? It's an absolute minimum because it is the lowest y value on my graph. It is a relative minimum because my graph changes from decreasing to increasing. This one, is this both? No, that is not both because that is not the lowest y value on my graph. With me? Okay, now I want to say something to you. Let me see if it's on. Do I have I don't have one. What if this graph was only defined from here to here? No arrows, endpoints. This graph would have an absolute minimum. Would this point be a relative minimum? A relative minimum means it's where your graph changes from decreasing to increasing. Does the graph change from decreasing to increasing there? No, that cannot be a relative minimum. An end point can be absolute, but not relative. I think we had one other thing I wanted us to look at, right here. No, we're not doing inflection. We'll do that next time, after the quiz. Absolute maximum is absolutely the highest point on the curve. X equal negative 2 is an absolute max. Now, just look with me. Give me the right term. What's this? A relative minimum. What's this? A relative maximum. What's this? Relative min. What's this? Relative max. What's this? Absolute min and relative min. Have a great weekend.